All right. So thanks for joining us. Thanks, Matt. Um, we'll go over some how-tos and some tutorials about ARC. I prepared some agenda, some items on an agenda. We don't have to cover all of them. We can do definitely whatever you guys would like us to go over. What I thought to do is first briefly look at how to install ARC with emphasizing servers, how to define them. Once you have that, you're good to go. Broadly speaking, we can look at all the tiny details. Then I thought to go over some scripts that ARC has to see how they could be useful for people. Then let's have an example of both thermal and rate calculation. I'll also show how to write an ARC input file, and we'll finish with a T3 example of running ARC, of course, with ARMG. So I'll share my screen here. All right. And of course, if you have any questions, feel free to interrupt me. And if you'd like to discuss something else, not on the agenda, feel free to let me know. So we're starting, let's see, with the confirmation search, conformational search in ARC. So we have the conformer module. And as you can see here, we're importing from species conformer, we're importing generate conformer. By the way, I didn't mention, all these scripts are already available on the ARC repository. So if you just go to ARC on GitHub under reaction mechanism generator, then we have IPython and that tools. So pretty much I'm going over these scripts, which we try to keep up to date with, of course, with the code base. So now we're doing conformers. So here it is. So I already loaded these modules. It doesn't take too long, but still to have that in advance. Give it some smiles, just whatever you want. Of course, as we said, the script is available, but we can go over what you can change here. ARC will have the 2D information, of course, from the smiles, and will generate a map of all different dihedrals that it perceives in the species. So if you look at it, we can rotate the OH here. So that's 1, 2, 3, and these are the 3 dihedrals with their respective pivots. And it will generate random conformers. Then it will try to perceive the wells. So for dihedral number 1, we'll call it, all the random conformers only had a dihedral angle between these values around 60 degrees and between that range about 300 degrees. So we know that whatever final conformer we're looking for the lowest energy conformer, whatever final conformer we end with, will have its dihedral either here or here. So we average these wells, and we don't know the energy, so it's not a scan, but we do know the wells, the location of the wells, and we do that for all the dihedrals. Sometimes it's not that well defined. As you can see here, we have some points here that got merged. That dihedral could be conjugated, could be complex, or it could be that we don't have enough sampling points, and maybe these two are one well and not two separate wells. That could be, and we can change that if we change the number of conformers that it randomly generates. And I don't see it here. Let's see if we can bring that up somehow. Shift tab to see the signature, as Matt told me, and I need to refresh myself as well. So here we have a number of conformers to generate, and it defaults to none. Then it takes a default from whatever the module has. Let's bump it up. I think the default is it scales with the size of the molecule, but we can see that it took 500 conformers. Let's see what happens if we tell it to take more. It will take a bit longer, but let's see if the map will be a bit different and maybe better. But either way, for that small molecule, we'll get a good conformer either way with whatever option we have. So we're waiting for that. While we wait, we can maybe proceed to the next script and come back here and see the result and see that we get conformer, and actually that model will return a list of conformers. And that list will answer two criteria. One is just a number of conformers, the number of lowest energy conformers you'd like to have returned. And the other one is energy. So here we have it set to 5 kilojoules per mole as a threshold. And it will take is it the union of these two? No, it will take just the lowest one, the most restricting threshold. It will just use that and return the respective conformers. So here we see pretty much the same map, even if we bumped up the number of random conformers to generate, which means that the number we had was pretty good, and we have some nice heuristics to scale that. ARC returns the lowest force field. Well, force fields don't say much. Of course, you'd like to DFT it, and probably if you want to really be certain what's the lowest conformer in terms of energy, you should use a nice method for the single point after you optimize it. Couple cluster or DLP no if it's very large, to be certain what the lowest conformer is. So here in the script, it plots it for you, and you can take a look. You see that it makes sense, right? We get a hydrogen bond between the peroxide and the oxygen, right? Oxygen radical, right? And so alkoxyl. And we can have different conformers, or here, maybe for that example, we didn't get that many different conformers. Let's do one final thing. Let's enlarge that scale a bit. And try just to see that we get something interesting. Here we're still using 500 conformers. We get a nice scan. Still working on it. It tells us that there are 900 hypothetical combinations here within the map. If you take the combinations of all the red dots, it will calculate these combinations. If there are less than 1,000, it will calculate all of them. If there are more, it will use an algorithm just to try iteratively to get to the lowest one. And we should get different conformers. I hope these are different. Are they? Yes, right. You can see that tail goes into the page and that one goes out of the page. And they definitely have different energies, as we can see here from the force field. But force fields aren't that accurate, so you should also DFT them. So that's that script for confirmation. I think it's helpful, and there are plenty of applications for it. One for solvent corrections. So if you're using Cosmo, maybe you'd like to generate conformers. Another, if you want to use, instead of transition state theory, you want to use multi-structure transition state theory. So you need to know the conformers as well. For the reactants, products, and TS, we're working on that as well. Oscar is working on conformers for TSs. Of course, let me know if you have any questions. Feel free to stop me. I'll go on. We have very nice tools for working with coordinates. I think I use them outside of ARC for just manipulations I need to do. So that's the script that is given with ARC, as you saw on the repository. Let's see just some examples, but then let's make something live and interesting. If you give it a string representation of XYZ, right, you all know the format, and you say check it and then print it, it will convert it to ARC's internal dictionary representation. So we have tuples of tuples for the coordinates. So we have first atom, second atom, third atom, right? And then XYZ, XYZ, right? So these are the coordinates. Then we have the symbols, and you can also give it different isotopes, but by default, it will take the most common ones. You can return your dictionary to be a string again. So that's that. We also have the formal XYZ format of an XYZ file. There's our Wikipedia entry for that if you're interested. So it goes by the number of atoms. There's then a comment in ARC. When ARC saves these files, the comment will be the level of theory that was optimized now. And then, of course, the coordinates. And what else is interesting? We have ZMATs, so internal coordinates as Z matrix. And the coordinates are a bit different, as you can see. And we can go over it, but I think it's not really relevant for now, but if it's interesting, we can go over it. But let's do something just nice. So that was already imported. You have that in the script in the repository. On my other screen, I'm just going to copy a path to a random file. So path. So here's a path for a frequency job of some file that was done actually in P3, as you can see here. First, let's see what that is. So let's visualize it. So if we want to visualize it, let's, you know, we can simply do that here, right? Let's visualize it so we can get path is that. And then let's do show sticks. So show sticks path. Hope that works. Yeah. So that's our species. Ethane. Ethene, right? Ethene. How do you pronounce it? Ethene. C2H4 anyway. That's what we have here in the file. And if we want to, and I think that's useful again. So you have a Gaussian optimization, frequency, whatever file. All you need to do is ask it to do SDR XYZ from SDR. So that would be, let's see now. SDR, no, SDR to XYZ. Why don't I have it here? All right, so we can check the dictionary, but let's see if I can import XYZ to S. All right, here it is. Sorry, got confused. So that's what you want to do. The names should make sense. So you know you have an XYZ file, and you want to convert it to a string representation. So XDR to XYZ. That function is very flexible, and you'll see that in Arc as well. You can give it whatever input you want. You can give it a string input, like we have here, right? Just a string input. You can give it an XYZ dictionary. You can give it a file path. Let's try before I just make up things, and hopefully it works. So yes, here it is. I gave it a path, and it outputs the SDR. So that's XYZ to SDR, and you can give it whatever you want. Again, you can give it the XYZ dictionary. So I think it's nice, and you can also print it. So pprint, I have it imported already, pprint, or you can do PA format as well. And so here's a nice print. That's not that nice. That might be nicer. All right, so here's a nice print of the XYZ parsed from the file. And now you can do whatever you want with it. So if I, instead of printing it, let's save it to XYZ1. And let's say you want a Z matrix, so you can do ZMat from XYZ. Right, and let's print that as well. Here's my ZMat. It doesn't look that good because it's a dictionary. So here, let's do the pprint trick. And here's the Z internal coordinates for that file. Of course, internal coordinates is something that you can have several representations, several internal coordinates per matrix per species. Here we take the starting point by some heuristics. So we want to start from the tail, for example, but you can also direct Arc. If you'd like, we can look at that as well. How to generate that internal coordinates matrix if you care about it, because if you want to change a certain dihedral, stretch a bond, or change an angle, it's very, very critical what you specify in how you build the ZMat. So we have that implemented as well. And you can go back and forth. As you can see here, you can generate the XYZ file format and pretty much go back and forth between every format. Another nice script is a way to determine external symmetry in optical isomers. Now, the external symmetry works not bad for a majority of species. Let's run it. So I have the inputs. Optical isomers could definitely be improved. So don't blindly count on it. You should always check. So here we see it says the external symmetry for that dummy molecule is 1. Makes sense. It's not a symmetric molecule. Optical isomers are 2. Let's see, do we have a chiral center? Yes, we do. That carbon here is indeed chiral for different groups in hydrogen. And here's the molecule. So that's also available online. It's useful if you just work with Arcane or want to get that information fast. Again, check it. Check the optical isomers. They're not terrific. It's based on a relatively old code that the QM module in RMG uses. And we have a way to make it much better, but not for transition states yet, because that new way is based on RDKit. So we're not running to implement it, but hopefully in the future we'll be more robust in determining optical isomers as well. So next script you can look at, and here is perception. That was the module was written by Colin. Here we'll have 3D coordinates, and we want to see the 2D graph representation of the molecule. So we already ran it, and here it is. Here you get the SMILES or the RMG adjacency list or whatever you want to print. Pretty much you get the RMG molecule object from XYZ. That's useful if you were given by a collaborator some 3D, some optimized molecule. You want to run torsion scans, so you need to know which bonds are single bonded, and for example, or you want to pass it to Arcane and calculate thermal. But the problem is you need bond corrections if you're using bond corrections and not other schemes, and for that you need to know the bonds. So that's generally useful. Here we have plots. We already visited that page several minutes ago. Plotting 3D molecules, we have several ways to do that. So here's our dummy molecule that we're using for that script. You can, of course, do whatever you feel like. You have show sticks, which is really nice, and you can play with it, and large, right, you can change it. For large molecules, it works very nice as well. And we have something we added. I'm not extremely proud of it, but it's something, balls in space. It's not dynamic, you can't rotate it, and I wish we could. That's something we're missing, and I wish we had a feature where you have atom labels or numbers, and you can also rotate it, like you can do, for example, in Gauss View or any other electronic structure software GUI. That sometimes comes in handy. All right. But again, that's nice, right? Just give it, the input is so flexible. So give it whatever you want. Give it XYZ, give it SMILES, and ask Arc to make your guesses with conformers and then feed it here, or give it a file path to an optimization or a Gaussian or MOLPRO, whatever input file. It will just read it all in and will parse it correctly. If not, let us know. We can visualize rotors, so I'm not going to run it. That's precompiled. It's also available online. If you give it a file path to a scan, currently supported are Gaussian and QChem and maybe TerraChem. It will plot it. That's nice. It can also plot and visualize a 2D scan for you. To do that, what will you need to do that? So pretty much, I think, yeah, looks like the path here is a YAML file generated by Arc. So that's a bit tricky. It won't just visualize 2D scans for anything you want. It will visualize a 2D scan for an Arc 2D scan. So you'll already have that file by default. Arc will save it. If you have a 2D scan you made, you'll have to load it in some Python way and dump it in the ARC format, and you can look in our API how to dump it into a YAML file. Then you'll be able to plot it. And you can change the color map and whatever you want, resolution, and have nice figures. Another cool thing about it, you can say you want to know how the conformer looks like at that well, or at that peak mountain, or at that shallow well, or whatever. You can give it the coordinates. So you can say -60 on -60, or -120 on 0. So give it the coordinates phi1 and phi2, and you can see here also the heat walls. So that should be done where? Here it is, yeah. Just give it the coordinates phi1, phi2, and run it, and it will draw it for you. So you can visualize it. Just nice how it looks like. Also on the online script, you have all the optional CMap arguments you can pass here to just make the image to your flavor. So that's all about scripts that come with ARC and could be handy outside the context of ARC. Before we continue, let me know if you have any questions or anything else you'd like to discuss.
Alon,
Yeah.
the kind of 2D energy scan for dihedrals makes a lot of sense for something like ethanol, where there's really only 2 dihedrals. How does that work for larger, more complex things?
Yeah, perfect. Excellent question. Thanks. For larger, more complex things, depends what you want to achieve. We can talk about 2 aspects: how to plot it, how to represent it, and how to actually scan it. So how to plot it, I don't know. I know 2D. Actually, we can think about how to plot it in 3D. It's just going to be complex. I don't know. But the real question is how to run it, how to execute the scan. Later on, you can take just a cross section of 2 rotors you care about and plot them. To answer that again, there are several answers. So if we stick to scans, ideally, but not practical, you can just scan all the torsions, right? And conjugate all of them. Just too expensive. And we would like to have an algorithm, and I think Matt previously wrote one, but we haven't implemented yet, that will tell us which rotors are conjugated, which rotors care about each other, if they're H-bonded or anything else. Then we would like to run them conjugated, and everything else we can leave as 1D, and that could be a very okay assertion to make. So that's like one aspect of the answer. I hope it helps. The other aspect is maybe if there are too many conjugated rotors and the picture looks too complex and it's going to be too expensive, of course, to run all of them, maybe don't run rotors. Instead, use conformers and Boltzmannize them, both for the reactants products and TS if you're running a reaction, instead of doing that. So that was, I think, my 2 cents here. Let me know if that answered the question.
Oh, yeah, no, that's a
sure.
Perfectly good answer. I wasn't sure if there was, underlying ARC approaches for those other cases already made, or if like good answer. Thanks, Alon.
Thanks, Chaz. Just another comment. Currently, we don't have partition functions. We can't calculate in Arcane partition functions for 2D or high ED waters anyway. So it's nice that we can scan them, and it's nice that we can plot them. But currently, we're not processing them correctly for thermo, and we should add that in the future, or just use Boltzmann averages. So we went over the scripts. If there are any other questions, let me know before we continue. So I saw some people joining, so I'll just say what I said in the beginning. I plan to add this video to ARC's documentation, in addition to another one we have from a year ago with another demo. So that will be available as well if you missed something. So feel free to interrupt me if you have any questions. We went over scripts, and scripts are available online under Archive Python tools. We went over some of these. And now let's go to see an example. And this example will set up some species, and we'll try to run a reaction. I won't actually execute it, but we'll see how to define things. So I have my imports. I'm importing the main Arc object. I'm importing species and reaction. And maybe the first thing we'd like to do is define our species. So I can say species 1 is Arc species. I have to give it a label. Arc demands a label so it can complain if there's something wrong. It likes to complain. So if you don't give it a label, it will complain as well. So let's say, I know already what reaction I want to run here. I have some peroxyl radical. I have smiles for it. And the way you can define a species is really diverse. So you can see that in the online examples as well. You can pass an RMG object. You can give it edge list, smiles, inchy, XYZ, just whatever. So here I have smiles. That's my peroxyl radical. All right, so species 2 will be, and now it's going to be an intra-H migration. So I'm going to have a CH2 radical. I'm copying the smiles from the other screen, and here's the correct smiles. By the way, let's visualize it, right? So let's see what are these species. So I can go.
Alon, you may want to change the species name. You have 2 species 1 right now.
Thank you. Thanks, Howie. Thanks for the comment. Absolutely. Species 1, species 2. Let's visualize that. So let's take our peroxyl, just see how it looks like. So I have smiles. So if I have smiles, well, of course I can make an RNG molecule, but if I want to see it in 3D, so let's go here and generate conformers for it just to see how it looks like in 3D. So it uses 1,000 random conformers to generate the map. All right, it can't, because it's a peroxyl radical, RDKit is having troubles with that. That's an issue we know about. I'm gonna cheat here and make it a non-radical, so we will use RDKit because the algorithm works best with RDKit. It defaults to open bubble. It will work, but it will take longer, and I couldn't solve that, so it can take 30 minutes, and we're not gonna wait for that. So I cheated, I added in hydrogen. It's not gonna be the right conformer, but I just want to visualize it to myself to see how it looks like. Here we have more than 1,000 combinations of all the red dots after it generates the map. So it will use an algorithm to deduce the lowest conformer. If we have several diastromers, it will show all of them unless you ask for a particular one, which is another nice feature. You can tell when you run an actual Arc job for thermal or rates, you can tell it which diastromer to use. And sometimes it's important. So here's our species, should be a peroxyl radical. And we should get that. So if you want to visualize the other one, then alkyl or CH2, so we can see it in 2D, and we'll get the conformer. So we'll wait for it just a second. 2 chiral centers that it identified. 2 chiral centers because, of course, the carbon here, but also that nitrogen. Not that one that has 2 H's, but that nitrogen is also considered an umbrella mode, so a chiral center as well. So here's the diastomer. Here are the diastomers. So that's one. You can see, like we have RS notations, but we also have NS or NR notations for nitrogen. It will also consider double bonds, which are chiral non-atom centers, so chiralic non-atomic centers. All right, we don't have to wait for it, but here it is. So here's what it deduced in the first iteration. It will continue for the other TS domain. So here are our species and intra-H migration reaction. We'd like to run thermo, so that should be enough to define the species. Soon we'll define the main arc object. And next, we'd like to define a reaction. So that could be the way we define a reaction. We should give it a label. And the label is special. The label should not be something like reaction run or something like that. The label should correspond to the actual species you care about. When you define a reaction, you can look at the API. I'm not going to cover everything right here. You can define it in various ways. You can just give species objects from RNG. You can just give an RNG reaction object. So it's flexible. But the default way, which is, I think, convenient or intuitive for users, is to just give the reactants and products if you have several. So you have plus something, but here we don't have several. And you make, and so it has to be, there has to be a space. The arrow has to be double-headed with an equal sign, of course. But that's why you define it. And it already knows these species will be in our scope. It knows to grab them, and that's it. So that's how you define your reaction. If we were in the future right now, or if that's recorded and you're watching us in, I don't know, 2 years, hopefully, we'll have TSS by various means, hopefully less than that, but don't want to commit. So currently, we do need to give the manual TS guess. So here's a TS guess that we have. We can visualize it soon. So so here's what I'm giving here, TS_XYZ guess. If you don't know the syntax, so Shift Tab in an IPython notebook, and you can see exactly what you need to specify with a doc string and all the arguments. And of course, look online or the API to see exactly how to define a reaction or a species. So you give it your guess. Let's visualize it. So, not perceived, sorry. Zoom has its toolbar, so I can't click anything I want. And plot 3D coordinates, yeah. So let's plot sticks for TS. Let's try, it doesn't always work because it does need an RNG molecule, and maybe I'll need to change branches here and then it will work. Let's see, I think it will work. So we can just say, so here we have XYZ and we have a string representation. Let's switch it to XYZ equals the path to our TS and see if that works. And now we have XYZ, and now let's show sticks of that XYZ and see the TS. And that should make sense. I mean, you don't get, you don't really see that dashed lines between the peroxyl radical and the hydrogen and a dashed line here, right? It doesn't go to that resolution, but if you know what you're looking for, then you do see that that hydrogen, if it leaves, it forms a planar CH2 radical here, or if it goes back, we have a radical peroxyl radical here. So that's nice to look at TSS as well. I do think Gauss view is better in terms of the representation. But if you don't want to get out of Python and you want to tweak angles or work with your TS, so that's a nice way to go. Let's go back to our example. So we have our species and their reaction. I should mention that the TS guess was generated by Duminda. So thanks, Duminda, if you're watching later. So I defined the reactions, and now we're going to define the arc object. I'm just going to copy paste from what I have here on the other screen. And before you run arc, you should tell it which servers to use and what job types to execute. And here we have some other tweaks as well. So for example, I'm going to use one of the servers to run an MIT server to run Gaussian. And I can run it locally if I have Gaussian on my machine. So job types, we have defaults for everything. So you don't really have to specify job types, but I want to make sure that I know what I'm running always. So I always specify job types. So you can see that Arc will generate conformers, will optimize, will use a fine optimization for your DFT level. If you're optimizing a DFT, will run frequencies. It will not do bond dissociation energies. It will run your single point energy. It will run rotor scans, so 1D rotor scans if you don't specify anything else. And here I don't ask for IRC. Let's ask for IRC, internal redundant coordinate. And we're doing that. So once that's set up, we're free to define our Arc object. We should have just one of that per project. Give it your project name. I pass species and reactions, right? So that should be a list. I think it might also work if you don't give it a list, and it will check the type. If it's not a list, it will make it so, but it should be a list. We pass our electronic structure software settings, job types, then give it levels. We can talk about levels in a bit if you'd like, and Kevin mentioned that, so I think we should. What's new about it? So I'll leave it for the next. In a couple of minutes, we'll talk about level of theories, how to define them. But here I just give opt level and SP level. If you don't give frequency, so it will take the optimization level and use that for frequencies and for rotor scans as well. And you can of course specify them if you want them to be different. They should ideally, theoretically, be the same. You can specify IRC should also be the same as opt. And that's pretty much it. I think you're all set. And now we'll use a final trick. I'm not gonna run it because the machine I'm currently on here is not actually connected to that server. What I wanna do for a large job, I wanna run it on the server. I wanna have an Arc input file, but I'm not native in YAML. I can write it, but if I need to write a lot of stuff, it might get out of hand. So there is a nice sheet. You can tell it to dump your objects here as a YAML. So you know what? Before you do that, maybe let's see how to execute it. I'm not going to execute, but just to see how to. So you should say arc object dot execute. And that's it. And it will run everything for you. And there's another video that should be uploaded to the documentation as well that shows demonstrations. Currently, I don't wish to execute it. I just want to save the Arc input file, and I'll copy it to the server and I'll run it there. So I make sure that I'm going to run Gaussian locally. You can also have the server spawning jobs on other servers, so you can define it here. And that's it. So let's see. Let's run that. It says like it's running Arc because you just spawned the Arc main object, main class. It's not actually running, and then it says that it wrote it to wherever you told it. And if I'll open it here on the other screen and drag it to the shared screen, here it is. Oops. All right, here it is. So here's our, all right. So here's the automatically written input file that we have. You see you have much more stuff here than you defined, and that's okay. So that's all Arc's defaults. It just dumps it. And here's our settings for electronic structure software, Gaussian local. You can see that frequency level was defined just like opt level. Let's look for opt level alphabetically. So here's opt level, Omega B97XT, F2, TZ50, same for IRC, same for freq. Should be the same for scans. So rotor scans, your scan level, here it is. SP, so you can do fancy stuff, right? I just changed the basis set, but you can do, of course, whatever you want. And then if we look at species, then we'll look at reactions. So let's just look for species. So here it is, species. We have our two species. It already has bond corrections. So it just enumerates the bonds, and then Arcane will apply bond corrections. And some descriptions that it will automatically dump in the thermal library. It's not complete. It will add stuff to it, like the optimization level, trouble it had with rotors and things like that. RNG molecule, multiplicity, and everything was already defined here for us. If we look at the reactions, So species, SP level, here's R, and here are reactions. We have one reaction in our list. It already has the charge for the PES, and still doesn't have the family. We didn't run it, but RNG will identify the families intra-H migration. Here's our label, and reactants and products, right, as we defined them. And the TS guess is a list. You can pass it whatever you want. You can pass actual XYZ strings, or you can pass files, and you can pass a mix of these. And I had one here, and that's pretty much it. So that was the example of how to define species, how to define a reaction with a TS pre-made manually, and also how to dump everything into an input file that you can later run on a server. So now I plan to do two things now. First, I lied before. I said I'll show how to define settings and define servers, and I just didn't, so we'll do it now. And one more thing, we'll go over how to define a level of theory. So
can I actually ask just a quick question, Alon? I was just curious. I guess, are there any advantages to running execute in the notebook like you were about to show versus like kind of creating the file?
Yeah, good question. Notebook versus the file. So first, if you want to run on the notebook, you can only do it from your machine, right? And of course, not from the server. Sorry, why? Of course, you can run a notebook on the server, definitely.
Yeah.
So run it from a notebook. The pluses here are that you get nice visualizations. So like we just saw for the species that you can play with them, right? So you get it in the notebook. Why run it otherwise in an input file? There aren't any downsides to running it as a Jupyter notebook, I think, unless it's just on your computer and you shut it down. So Arc itself will the Python software Arc will terminate, but all the jobs are still running on the server. There's a restart feature that you can run, but it won't spawn anything during that time. And also, I just like it. If I have lots of jobs, I would like to have all these tabs open. I just like to have it on the server, but just your preference, whatever you want.
Thanks. And then just as another quick follow-up, going back to the Arc example, that tab where you were writing the input file, are there any other, I guess, defaults you think we should be aware of? Because I think sometimes I struggled writing input files with the right syntax when it changed. And so it seems like if I were to use this script, that would solve all of those problems for me, because it would automatically write it in the correct format with the right level of theories and whatever. So I guess just, are there other things that you think, common users should be aware of, that other options that we should know? Because it printed all the default options. We only went through a couple of them here.
Nothing that really comes to mind. Like you're referring to defaults, to other defaults not covered here.
The ones that were printed, yeah, like all these. If there's anything that you think is worth covering, I would trust your judgment on that. That's all.
Mm-hmm. Let's see. So we can go over some here, but nothing that I think is really crucial. So for example, by default, it says calc frequency scaling factor true. If Arcane doesn't have a frequency scaling factor for you, then it will spawn jobs and use the Troller method to deduce the frequency scaling factor. And that could spawn jobs of species you didn't ask for. It doesn't take long. Usually it takes about 15 minutes for a nice TFT level. But just be aware that that's true by default. And some users are surprised or open issues. Hey, why do I get these molecules I didn't ask for? So that's something to know. Let's see if we can find anything that might be interesting. Currently, we only support Arcane. So one thing I can note that we didn't cover, we have adapters, right, for StatMech. Currently, only Arcane is implemented. We plan to implement MES and MESBER. And then you'll have a kinetics adapter. It defaults to Arcane. And you should also have a thermo adapter. It defaults to Arcane. Thermo should always be Arcane because Arcane has nice schemes for corrections. But kinetics adapters could be in the future whatever you want. So just note that that's what it defaults to. We'll cover levels of theory, but I don't think there's anything else special that should be mentioned.
Sounds good. Just wanted to check. Thank you.
Yeah, thank you. Thanks, Ken. Any other questions before we proceed to levels of theory and then settings?
I got a quick question.
Sure.
So when you set rotors equal to true, is that performing rotors on both species and transition states?
Excellent question. Let's see. I think so. We recently merged a capability to run rotors for TSs, and you can see that here when we press command zoom toolbars. When we didn't do that? Here, when we plotted the TS, we do have an RMG molecular representation for the TS, and we can see where the single bonds are. So we do run TS rotors. I think it does that for TSs as well by default. I'm not entirely certain. We can check, but the intended behavior is that it does. Yeah.
Okay, thank you.
Yeah, sure.
Are there any challenges in getting those scans to converge? You optimize each step of the dihedral to a saddle point as you're rotating around the rotor for a transition state. Is that right? Or
yeah, so it's a scan opt equals TS, right? When we run it in Gaussian, so we're it's a constrained TS optimization at every step, right?
okay,
right.
Cool.
There are of course lots of challenges.
Yeah.
So Shori, a PhD student from Bill's group, worked quite a bit for a troubleshooting module in Arc, which works pretty nice, and to freeze additional dihedrals if you need, or to try to do lots of tricks to get the scan to converge. He had a nice test set of several hundreds or more species, I'm not certain, and got all of them to converge with pretty funky functional groups. So that's nice. What does it mean? Is your scan good if you constrain other dihedrals as well? You know, these are assumptions and we don't have the answers for that. But implementing his scheme, we do get nice conversion, at least for, or after we troubleshoot for all these scans. I'm not certain if we have that covered for TSs, we can check, but for stable species, definitely.
Cool. Thanks.
Sure. Any other questions before we proceed? So let's talk about level of theory. Let's see the API. Let's see if it's helpful, and then see if we want to define or just look over the YAML file. That's helpful as well. So what did I just do? Yeah. GitHub just changed itself, right? Did you notice that in the last week? All right, here it is. Here's our documentation. If you look at the API, I want to see the level of theory. We have a module for that, and here it is arc.level. That's how it's defined, and here are the parameters. Let's talk about that a bit. First, the motivation was a change in Arcane, and Arc should be compliant with Arcane, and Arcane has new demands. Sometimes it requires the software when you give it a level of theory. For example, Omega BNT7 XD, you can run it in QChem, you can run it in Gaussian. If you have bond additivity corrections calculated using calculations in Gaussian for that BFT level, then you'd like the bond additivity corrections and atom corrections to fit to your exact level and exact software. They also have slightly different syntaxes in QChem and Gaussian. And there are other instances as well. So since Arcane changed its requirements, so Arc adapted as well. So now we have a level class. So you give it a method, right? Like Omega. Let's see, do we have examples? Do we have examples? maybe in the documentation elsewhere, we may have examples. Yeah, we do. We can cover that in a second. So you give it a method basis set. If you have an auxiliary basis set, give that. If you have dispersion not specifying in the method, you should give that. Complementary aux for F12 calculations. I never got a chance to use it, but Arcane has that feature. We added that as well. The method type, whether it's DFT, wave function, force field, or whatever, it will be automatically derived by Arc. Really, all you have to, so the required attribute here, required parameter is method. So we have parameters and not args. So method is required. You can give CBSQ3 and you don't need anything else. If you give basis set as well, right? So usually people give method and basis. Everything else is really optional. So software, if you want to force it to use a certain software, you can do that. You shouldn't usually. It will derive the software automatically. Arc will derive the software automatically and pass it the correct software to Arcane. Software version, it's never been used, but it's there. Solvation method. So if you run and you want to run a reaction using some solvation correction, PCM, SMD, or some more sophisticated schemes that we can touch upon if you'd like. So you specify a method like SMD, your solvent, like water as a string, and here are some examples. There's also a more advanced scheme. For example, if you run Orca DLP-No, they may have solvation corrections, but not exactly what you want. So you can also run your molecule just single point in Gaussian, and Arc will do that for you, with and without SMD, and just take the difference of the correction for the solvation and use that and append that to your DLP-No single point. So here's the solvation scheme. You'd still need to give the method and a solvent, but if you give it a scheme, which is a level class, then it will spawn these single point jobs. And that's pretty much it. There are compatible software that it derives by itself. So that's how we define a level. I know it's not that clear because it's not an example. Let's see examples, and I think it will be clearer. So how do we define levels? So first, you can define a string like you used to, the old nice way. Just say CBSQ3, just say a single point / BFT, and it will automatically derive all the level classes for you. We should have an example. I haven't prepared one, but let's see on what page. I'm sure we have somewhere. Let's see, and here it is, levels of theory. So these are the levels of theory for different job types. And then that's how we define them in Python. So your conformer level, or just whatever you want, right? Define your method, your basis, and the dispersion, and you're done. And you can also have auxiliary basis set if it's DLP-No and you would like to use one. Some arguments, so DLP-No, you want to do type P-No, normal P-No, and you can set the SCF convergence, whatever you want. So it's all explained here, how to specify that, whether it's a keyword that Arc should just append to the first line, or whether it's a block that you want to add somewhere in your input file. So you can specify either keyword or block. And here's another example, simple example. Anything else interesting? So I think that's pretty much it. And here's an example for a block argument that you want to add. So you can say type P-No as a keyword, and then as a block, a general one, the word general will not be used. And then you give here, you see 2 lines, SCF dry run true, then end. That's how Orca requires that input to be given. So you can add multi-line strings as well. And of course, any IOP keywords you'd like to add to Gaussian, you can add it as well. So everything is in level now, the software, the keywords, and I think it's nice because you define that level object per job type. So for example, you define it for an oct level, or for freq level or whatever. So you can have really precision of where you want that keyword to be added, to the op, to the SP, to which software, so you can control all that. Let's see a final example, and that will be the input file we just generated together. Let's see what was dumped here. Let's see, for example, frequency level. So we have our method, right, omega B97XT. It knows already that it's a DFT. It knows the software should be Gaussian because there was no dash here, I think. QChem has a dash and Gaussian doesn't. Here's our basis set. Here are the compatible ESSs, not QChem, but you can run that in TeraChem and it will run. And that's pretty much it. So before we cover settings and how to install, again, let's open the stage to additional questions. All right, so I'm switching screens here if I can. I'll share my other screen. Did it work? Yeah, it did. All right. Great. So what we're looking at is the settings.py file in Arc. So it's under the Arc repository, under lowercase arc and the settings.py. That's really what you should change when you install Arc. The installation instructions are online, pretty much clone the repository. We don't have a Conda or anything else package because it's still under heavy development, and we still recommend to use the ARMG repository, like the installation for developers, and not the package, because we're using the latest version of ARMG that we'd like to be compatible with until things relax, and then we may have a package. So you should clone the repository from GitHub and add it to the Python path, and everything's detailed online. And here are instructions for how to define servers. And that's an example, a commented out example of what you should do if you're at the green group, for example. You want to work with Ferris and the ARMG server. You should specify the cluster software, either Oracle Grid Engine, used to be called SunGrid Engine, still called SunGrid Engine. So either OGE or Slurm. That's the only cluster software Arc currently supports. We can extend it if needed. Add, of course, the server address, your username, and the RSA SSH key to be used. So it's a dictionary that goes by the server name, but there's another reserved keyword, local. You should not name your server local if it's not local. Local means that that's the server, that's the machine Arc is running on. And if you want to execute Gaussian, you shouldn't SSH a different machine. You should just SBatch it. You should just submit it on that machine. So we use a different module to submit the jobs. It's transparent to you, to the user, but you should just define it correctly. You should still give a username, because Arc uses that when it does QStat, for example, to check the status of jobs. It will add a -u to just get the status of username by the username. We can also deduce it automatically. We haven't, it's not that important, but just note, you shouldn't give the address or an SSH key, right? But you should give a username. And of course, the cluster software. Once you've done that, there are additional optional parameters, CPUs. So the number of CPUs you'd like to use per job, that's not the maximal. It could be whatever. I can just say 20. If I don't want to occupy an entire node, or 24 to be half, and just occupy half a node. So that's actually what will be used, but memory should be the actual maximal memory that you will ever allow Arc to use. So if Arc is allowed to use a full node, maybe write the total number of gigabytes you have on that node, whatever that is, just give the maximum. Arc will never use more than, I think, 90% out of that. And it doesn't even start there. It starts at some other default you can specify in the Arc object. And if needs, then it will troubleshoot and it will bump the memory. according to what it sees in the error file, in the log file, but it will never pass 90% out of that. So that should be the maximum. But if you want to use just half of the node, so maybe do half of that. That could make sense. That's the majority of what you need to do. In the installation instructions, you will also find instructions for how to change global ESS settings. Where is your software located? So I have Gaussian both locally and on some servers. So if Arc needs to run Gaussian and it has local first, and it says the local server, it will spawn it there, and so on and so forth. It could be a list or just a string. Another interesting thing is a combination of levels of theory and the software, the ESS, the electronic structure software, that will be respectively used. So here we just give a fragment, like VPZ. I don't know why we have that under Molpro. We can, of course, run it on other ESS as well. But MO6 to X without dash should be run only on Gaussian, and maybe Terracam as well. MO6 dash to X should be run QChem, for example. So if you just give fragments like that, you can run them respectively. Of course, Gaussian can do a couple cluster, but if you have Molpro and you want to do that, so that's the way you define, and Arc checks that first before its internal heuristics. So just be aware of that. I think that's the most important part. We have default levels of theory, they're defined here. You should define levels of theory per project, but if you just run a bunch of projects, you can set it here and not define them in your input file, and they will be used. Right. Additional settings, you can go over it, but they're less important. So I believe I covered everything I wanted. Let me know if you have any additional questions. And I think we're also pretty much on time. So let me know if you have questions. Wonderful. So any issues you have, feel free to post them on Arc's GitHub. Any features you'd like to have, post that as well, or collaborate with us. We're happy to do that as well. You know what? There's one more thing I want to show. We're a bit over time, so I can show it quickly. I want to show a T3 example before we summarize. And I have it here. All right, so here's a T3 example of how Arc works with RMG. I'll do it fast. I'll try. So here's the input file. You give it a project name. We have some options like what do you want to calculate? So that's before that, sorry. So first thing to note, we have three major sections to the input file. T3 stuff, options, sensitivity, RMG. So that's a new way to define an RMG job using YAML, using Python syntax instead of the RMG Python text-based input file, and then QM. And QM, we have an adapter. Currently, T3 only supports Arc, but we would like to implement AutoTST and have T3 support everything. So it's already set up to be modularized. So here in T3, we say calculate all core species. Here I ran a very small model, so I'm running everything. I limit the number of iterations. I can parallelize RMG, and I'm using RMG for the sensitivity. I can use RMS for sensitivity. I can use Contera for sensitivity. So that's the adapter I'm choosing. There are a bunch of additional arguments. I'm not going to go over it, but they are documented. You can check it out. Updated documentation will soon be online. Then in RMG, you'll recognize that it's slightly different. So we have the database block. So here are the thermal libraries. We renamed reaction libraries to kinetics libraries. Also, all the tiny tweaks, all the tiny things that are different than what we know in RMG that were done here are also well documented. So you can check it out in the T3's documentation once the updated version is up. I hope so. Your reactor, that's different. So we have the type. We wanted user to be aware of the reactor they're running. So that's batch, liquid, constant TV, so you know what you're doing. T could be a list. Termination time, that's in seconds. You can do whatever you want. Then you define species. So both are lists. It's not that well printed out. I already also used here an automated input file writer. So it's not that human readable in that without line breaks, but you can see my species. I have, so it's a dictionary. Let's see, it starts here and ends here. I have my label, I have concentration, and I have smiles. I can also give edge list, some additional nice things. You can make a species constant. You can make it not reactive like you do in RMG, but it's all like in one dictionary. For the model, you can give several tolerances, then T3 will use them by order for the iterations, and we'll just use the last one. Usually we don't use these low tolerances. We'll just use the last one for all the iterations it needs until it converges, and you can see all the other constraints. For QM, here, other than adapter, you give everything you give in an ARC input file, everything we covered. You shouldn't give species and reactions. They'll of course be derived from RMG, but you may, if you know some species in advance and some reactions that you want to calculate, just put it here. ARC will calculate, T3 will use them in the model when it feeds it to RMG. Let's see the output, and I think I'll be done with that. So here it took 8 iterations. Iteration 0, by the way, is that pre-ARC run or pre-QM run with a different adapter in the future that will just run thermal rates. Here's iteration 1. So what do we have here? First, it ran RMG. Here's the legacy RMG input file as you recognize it, the Python one. So we have a writer that writes everything correctly for you with the correct syntax. It just ran it, so I'm not going to explore the output. Then we have an ARC folder. So we don't have an ARC input file. We should, if we'll dump one, but it uses the API. We can look at the restart file. It might be large. It is large, all the species and just everything it did for the first iteration. And then sensitivity analysis that it ran for us. I'll conclude by just showing the log, which is a nicer capture of that project. So you can see when it was ran. June 16, today is June 26th, so 10 days ago. Here's my project. First, it spits out the input file, so here it is. So it's documented. And then iteration one, it runs RMG for you. It took 7 minutes, runs sensitivity analysis, reports the species, and it knows that additional calculations are required because we asked to calculate all core species, so that's all group additivity core species. That's also documented, the intention. So then it knows which species to calculate and why. It gives you smiles. Calls ARC, it took it almost 3 hours, and one did not converge, so it knows about it. Currently, we're not doing anything about it, so that species will still be in RMG. ARC will not try to, so T3 will tell ARC, or will not tell ARC to recalculate it. In the future, we plan to have a more sophisticated approach to non-physical species. That species is a peroxyl radical on a nitrogen that just broke during optimization. It's not a well. Then iteration 2, a bunch of other species, something did not converge. Iteration 3, a bunch of more species, and then everything converged. So all species successfully converged here, and blah, blah, blah. At the end, when you don't need to calculate anything else, you have a species summary. So everything it just calculated for you at the level of theory you chose. So here's CBSQB3, what failed, and you're done. 13 hours. But look how much work it saved us. All these files just running RMG, running sensitivity analysis. Here I did not use the sensitivity analysis. I just calculated everything. But principally running sensitivity, looking at the species, calculating them. So it's automated, but still you should direct ARC or whatever software to calculate them. Parsing that information, making a library, running RMG, see what you need to run now. And you can see that we iterated 8 times. So it's work being saved, and that's it. So I'm already over time. I'll take last questions, if anyone has about T3, but not before, I'll give a huge thanks to Kevin, who worked with me on T3 to take it to the next stage. So thanks, Kevin. And let us know if you have any questions. Sweet. So with that, let it leave issues and feature requests on both repositories, T3 and Arc. Thank you. I can hear you clapping. Thank you so much. I appreciate you joining us today, and hope to see you in person soon one day. I miss you all. Thanks so much. Thanks. Bye, everyone. And thanks, Matt, for organizing this.